And the way you do that for whoever might need to know is you record to your local computer to avoid the bandwidth back to Zoom, and then you process it on your own laptop. So welcome, everybody. And you're looking at the view from the parking garage at John Peter Smith Hospital in Fort Worth last Saturday for our microwave activity day. And we were souped in. So there was a couple of cell towers within a quarter mile that are not visible in this picture. It was about 10 a.m. The fog burned off and we had better visibility within about an hour or two and had a great activity day. This is a good place to work from as a rover. It has public access. You can go all the way up to the 5th or 6th level. It's not great when it's windy, but there are some covered areas where you can loop some bungee cords or you can get tethered to the concrete pillars. So this is what we've got today. I had asked for presentations. I know people are busy and I did not get any submissions. So we're going to do some replays from previously recorded presentations. But I'll start off sharing some experience I have with microwave filters. I'm not sure you'll learn anything in that, although I was surprised about a couple things along the journey. And I'm sure it's just starting, but when I think about some of the folks that are here in the audience and their 50-year experience that they've had or 60, I realize that, I'm like skipping a rock across a pond with my experience where they've paved the way, for decades. And I come across their names as I learn what I learned. So thank you for that. And I hope I don't bore you with what I'm going to present. But then we'll listen to Al again. He just did this presentation at Central States and also presented it here at NTMS on August 9th. And then Greg had a third generation 10 gigahertz transmitter. I thought it was interesting enough to replay back in March. And then we'll go on with the other things that we do. So without any delay, I'll get the presentation I've got going. Using microwave filters. So some filters that I have a little bit of experience with that I want to talk about are those created from component surface mount devices, strip line filters, hairpin filters, waveguide filters, and pipe cap. So the first thing that comes to mind, and as I was putting this together, is that on the WaveLab control board, we have a 2.45 center frequency SMD, and it's in a 1008 size. And this has good characteristics, as you can see, with the transmission profile and the return loss on the right side.
Jim, I'm not seeing the slides advance beyond the agenda.
Okay. Thank you for letting me know that. That means I need to do a better job of sharing. You can either share everything on your desktop or you can share individual windows. And so I've made that mistake. You should see the title slide now.
Got it.
Yeah, we see the title slide. Yep, using microwave filters.
Okay. And then here's the review of the bullet points, components, strip line, hairpin, waveguide, and pipe cap. And there are many others, or combinations thereof. Here is the Murata datasheet, and this is a SMD part that's on the WaveLab control board. The plots on the right side show us the transmission profile and the insertion loss, or I'm sorry, the return loss. You can see on the bottom table that the center is 2450 with a 50 megahertz bandwidth. It says about 2 dB insertion loss in the bandwidth, and then 43 dB down minimum on these certain skirt frequency locations. So it fit perfectly in the WaveLab. To note one thing, there was a directional input mark over here on the left where my mouse is. And we found that it didn't make any difference which way you oriented this filter. It's in the path right here's the schematic and the actual physical realization down here on the bottom. So on the bottom, U2 is the mixer. The coupling caps are C9 and C10. The TR switch that's on the far right is this black six-legged SMD right here. So the filters in between the mixer and the TR switch that will branch between transmit and receive to the module. So the filter's in play whether the signal is going from right to left, which would be transmit, or from right, I said that wrong, didn't I? From left to right would be the transmit signal, and right to left would be the receive signal. So the filter is used both directions. Murata has a number of other filters. I've looked through the list as I needed some for some modifications to the XN, X-ray Nancy, XN module. And they had what I was looking for. So there's, here's a component SMD with 2 dB insertion loss that could be used in the low microwave area if you consider 2.3 or 2.4 to be low microwave. This little assembly came up at Vancouver when we were up there. What's it getting to be, about a year and a half ago? They had implemented this board for Pluto, software defined radio, and it's 2 RF switches with a bunch of SMD filters in between. And you can see the part numbers down here on the bottom. So for the first 3 bands, 1296, 2304, and 3446. I don't know why that says 3446, but that's the way it was printed in the proceedings. It's fairly acceptable insertion loss, 5 dB, 5 dB, and 7 dB. But when you get to 5 gig and 10 gig, it's getting out of hand with 15 and 20 dB. Anyway, this fella had put together this board and ordered the parts. I think he said the little SMD filters were around $6 a piece. There's one wire here for a net error in the schematic. And then if we look at Amazon today, there is an actual filter that looks very much like what we saw a year and a half ago. It's called the New Elect filter, and it's lower in frequency covering 2 meters through 23 centimeters. The schematic looks very much like what we just saw, except for these bias T's to help supply power to these RF switches. And there is this in the middle picture, and in the left-hand picture, it looks like a switch that you would flip, turn right or left to select the path for the filter that you want from, one SMA connector to another. I don't think this would be very useful, but it could be on the bench or in experimentation if you didn't want to build the thing and you just wanted to order it. I suspect it's got more loss through, but I did look up this data sheet, and if you can believe the data sheet, it looked pretty good. So I want to talk about strip line filters. Demi, Down East Microwave, told us at Central States, when was that? Back in July, I think, that they're using strip line filters in a new design. And they mentioned Markey Microwave Strip Line Designer tool. So I took a look at this back when I came home from Central States. And it just kind of died there because it's lower in frequency than where I'm interested at that time anyway. But I just clipped a part of their page here so that you could see when you design, you specify the order and the type of topology. Over here on the left, this is a Chevy Chev 5th order topology interdigital cutoff frequencies, 1900 and 2100 ripple parameters, and it just doesn't. Tells you what it is. Now, it doesn't have a exportation where you could turn this into like a KiCad file or some other PCB recognizable file, but or at least the free version doesn't. And this is online. I mean, you can just call this up and start designing with it. These are really looking like optimized or perfect plot down here with these sharp corners on everything. But anyway, that's a very typical plot for a bandpass filter. Oops. Then I go on to hairpin here. Hairpin is like it sounds. And my experience has been with this hairpin that's in the WaveLab module. And on the left side, you see the 3.6 gigahertz bandpass filter that's in the module. And the height of that set of traces is 13 millimeters. And then the next filter in line is on the right side. Those are 4.5 millimeters high. That is a 10.9 gigahertz bandpass filter. And then the transmit chain final BPF right before the PA. It's actually before the pin attenuator here, but then following the pin attenuator is the PA. That is 23 gigahertz, although this one has been modified to 24. Those elements are 3.6 millimeters by 1 millimeter. So it's greatly magnified. If you look close, you will see where I have cut these filters on each end with a scalpel. I wanted to remove 0.15 millimeters from each side, which is not scientifically possible with a handheld scalpel. But through messing with it, I was able to get it to tune closer near what I wanted it to tune. Got to be careful working with an open module because you can see the wire bonding items on either side. This is really a strip line filter, at least I think it is. The substrate is 0.3 millimeters thick. And it's so thin that when you cut these traces, unless you're very careful, you'll go all the way to the metal. And just to point out where these are located, I've flipped up this slide that we've shown before about what happens inside the WaveLab module. So on the lower left, you have the LO coming in at 1.8 gigahertz. That is doubled and goes through to 3.6 gigahertz. That was the one that was 13 millimeters high. And then coming over, it goes through a tripler. And now you're at 10.9. And then this travels upward where it goes through this Wilkinson divider, taking the left branch, goes through this up converter and into that strip line filter, through the pin attenuator and into the 2-watt PA. The receive side's over here on the right side. It comes right in. This part right here is a down converter. It's a very nice part. It's also the same part that's in the Cooney 24 gigahertz transverter that they currently sell. And it's coming in here with the LO on one side and then pick off the sideband and back out to the control board. The size of this picture on my screen is about 4 times the size of the module in reality. It's very small. Another hairpin design, and this is a link that's in the document. Got several links here, but this is one of the W1 gigahertz published papers on hairpin filters, and I believe this is from the KK7B, maybe a transverter. This is going to be 902 or thereabouts. As far as design tools go, there's a MATLAB designer, and it is free. But, I mean, not just this tool, but anything that would discuss hairpin filters is going to have a learning curve. Was able to pull it up here after creating a free account, where they had a drop down where they asked what your orientation was, and I said hobbyist. So I was able to create an account and open the online version of MATLAB. And then there's this guy, Charles. He's got a website here. There is the link, Charles Labs Hairpin Filter Designer. And his approach is to prompt you for an element length and a center frequency. And then he will tell you what the footprint looks like. But I suspect that this might be, since he arrived at the Python code through experimentation, it might be only usable within a certain frequency range that he was interested in at the time. Whereas the MATLAB would be more able to consume a variety of frequencies and have the dynamics to bring you to a topology that would be appropriate or close. Here's something I have. I have 2 of these, and I don't know what they are. I think they're a combination between a combine and a cavity, but there's a whole bunch of tunable slugs on the side, but there's SMA. It's not a waveguide input and output. It's got SMA connectors on each side. But reading the label, I see 5.7/5.9 and 30 S11, which might be the return loss. Not sure. This one, I think, is definitely a combine. Here's some waveguide filters that Mott's KD5 Fox Zelta Zebra X-ray tuned these up for me and he tuned them to 24,192. The left side has 3 ports. And this was our initial 24 gig sectoral horn test that we had on the NTMS beacon. So there's ports on each end of the long side, and then there is a port in the middle. I'm sure this has got an interesting story, but we are using, you can see where Mott's marked IN on the middle port. And so when we were using it, we were inputting RF here on the in port, and then the out port, there's sectoral horn there. On the right side is the actual filter that we ended up using on the beacon. And this one was also tuned by Mott's. And that is the WaveLab module on the other end of this blue coax, where we're taking the 2 watts output and coming through the waveguide to reduce the LO leakage. It's pretty prominent on this WaveLab with the control board products that end up in it. And here are, we go into the pipe cap discussion. There are some early designs from Kent, and there's a link here to his paper. He was on this so many years ago with designs and plots that he had made himself, and then some with the help of Al. And the technology really hasn't changed. It just takes a couple of different forms, but it's still the same. W1 gigahertz has got a couple people here that one of the reasons I do these presentations and put the links in here is for me. Because I'm always calling these things up out of the NTMS website, because I like to stare at this stuff and I forget where I put the printout, because I usually print it out. And then it's just easier if I'm somewhere that I can't access my printouts to pull something up and give a look at it, to be refreshed with what it was that I remember seeing. There's 2 good papers here. One of them has the suggestion about using capacitor through hole leads to actually make the probes that go into the pipe cap on the other side. This is how I have built several. And you'll see on the left side, there's respect for Kent's approach with the coax input, and then also to the left, the PCB input. So I like to review this and look at this, and because I've made several just like this, where I had to, what I did was I would bend the capacitor leads after I got them to the right length or thereabouts, so that I could step away, and I knew that the probes were sticking down into the pipe cap cavity, and then bring the soldering iron to work on on this side where I had the clear lead. But it was never dimensionally perfect, and I guess there's a point where it doesn't matter, and it's all relative, and you can get close enough in the tuning to end up where you want to be. And here is the personal beacon and LO multiplier. Built a few of these, or one of these I've built. So you can see a reduction going in here from 3.456 with the big pipe cap is going to clean up what it can in that area, so that you end up with a multiplied, because there's underneath this board are mimics. So you're going to multiply and have products here out at 10 gigahertz which will be further tuned and filtered by the two smaller pipe caps, which are technically called half-inch pipe caps, but nothing is half-inch. It's more like 5/8 of an inch OD. But if you've built these, you already know that. And so this link is to the paper regarding how to build these, and has lots of good information in it. If you look at this PCB board, you can trace the inputs on the left side. You can see this ERA2 probably mimic, and then you'll see just a spot of solder. Oh, that's the probe. And the probe width, the distance between these two spots, is wider than these two spots as we move to the right. And what you're seeing is the underside of what is happening on this top side with these larger 1-inch pipe cap on the left and the, quote, half-inch pipe caps to the right. But I want to bring your attention to this SMA connector right here that's about a third of the way or half the way on the input. This is technically a test port. So when you build this first stage with the two mimics, the bias circuitry down here or up there, and you work to slowly apply power, do the normal DC checks, looks for a short, look for some current draw, ease into it, and look for amplification across this pipe cap through this input down through this point. And this capacitor right here, it's kind of hard to see, is normally oriented 90 degrees to the right so that the output of this mimic is running out this test port. This will permit you, if you'll input 3, 4, 5, 6, or at least noise that would cover that. So let's say you had a 1 to 5 gigahertz noise generator, or even less than that, 1 to 4, 1 to 3.5. Then you would tune this pipe cap while observing the spectrum on this test port. And that's what this right turn with the RF signal through the coupling cap when it's installed in this right-hand turn position. And then when you get this stage tuned, you move this capacitor back, and then now you can look at how things go through these final 3 stages of amplification across these two pipe caps by observing 10 gig output on this far right port. So that comes to play when we talk about our 10 gigahertz NTMS beacon, because that's what I've done here, is I've taken just the first stage to clean up the 3.4 signal. It was so bad. I mean, by that, I mean it had so many unwanted signals, spuri, before or lower than 3.4 and above 3.4, that I just said, I'm going to convert this one unit that I have into a 3.4 filter. And so I just took the output from the first stage by moving that capacitor around, and that cleaned up things very nicely. And now I was able to go multiply that output without bringing along all of the spuri that was originally there. Here's a schematic of that first stage. Very typical design. This uses the ERA2, I think it says there, but you can select what you need here according to both the frequency, where you want it to take it, and the bias requirements. And there is, I should say, this circuit is also operational up to 5 gigahertz just fine. So filters at 3 and 5 would be okay to filter through this kind of a application implementation. At least in my opinion, they would. And this takes us to the 47 gigahertz beacon that we have. We have a tri-band beacon. It operates at 10, 24, and 47. The 24 was hardly any problem, but the 10 and 47 have required some thinking. And Tom Williams, WA1MBA, has created a board that will provide 11.772 gigahertz filter. I'm going to digress on the next slide and show you why that's needed. But really, the story is here. The undesirable image at the LO minus 435 is 10902. Well, when that's multiplied times 4, well, first of all, 10902 is outside our allocation. But when you multiply it times 4, you hit 43608. That's well out of our allocation at 47 to 47.2. So this board means to clean all of that up and provide throughput for the 11772 signal to be amplified by or multiplied and amplified by the quadrupler. So let's digress and talk about the beacon. This was our genesis for the MBA board need. Same IF and LO frequencies I just presented. And this board worked, or this RF deck worked. It was WSJT Q65 decodable without any problem, but it had these other spuri that we don't want to let go out there. Those allocations are government allocations, likely the military. And it's good they're on our side, but we still don't want to be interfering with them. So the red box defines the components that needed replaced, plus filtered. There's no filter here at all other than the waveguide, I guess, right here. So this is on the upper right is the mixer, which is mixing the left to right IF signal coming from an amp through an amp, and the 11 gigahertz signal coming off the Cooney LO. And what's coming out here is 11.7 gigahertz through 2 amplifiers and then into the quadrupler times 4. And this was yielding the problem LO and the LO minus IF. So Tom worked on this. We worked on some of this together, but Tom decided to build a board, and it would replace the several individual components that were shown with the red box. That would provide the 11 gigahertz filtration and amplification, but the board requires 3 half-inch pipe caps, and those are located with these arrows, 1, 2, and 3. So his board would replace, if you follow my mouse on the left side, the mixer, the amplification stages for the RF side. The IF is coming in through the mixer, so that's a combined product. And then a final filter and 2 amplifiers to provide the RF out. The key point here is that this was going to require pipe cap filters. I had talked to a couple people about half-inch pipe cap filters at 11 gigahertz, and they told me it couldn't be done because the cavity was too big, or that it would be difficult to be done because the cavity was too big. So here was a solution. And I'm going to show you how I make pipe cap filters. And I'm going to stress that there are many ways to do this. And my way is probably overkill. So don't criticize this. It's just the way I like to do it. First of all, I get the center hole drilled and tap, and Mott's has done that for me. Thank you, Mott's. I've tried to drill this hole in the center, and I can't get it in the center. He uses a lathe, a big machine, probably 500 pounds in weight, but he gets them dead on. And then I get them back. This is me deburring the hole with a drill bit on the inside, just turning it a little bit. And then I have a fixture. It's a piece of wood, and it just captures a 440 nut down in it. I'd like to make this out of metal when I have time. But anyway, I just use cyanoacrylic glue to hold it in place. After it gets heated 2 or 3 times, it'll come loose, and I just stick it back down in there and put more super glue on it. But this captured nut will hold the pipe cap in its bolt assembly. So I screw down the assembly on the wood fixture, and I add flux around the perimeter. Try to get it about even. Excess is better than too little. And then I lasso the pipe cap with 2 loops of solder. And I use a little small flat screwdriver to push the solder down into the flux. Be sure that the solder's not up on the side of the pipe cap. Just kind of squish it down. And I wrap that solder around the edge of the board, which kind of provides a little friction or capture so that it won't be loose. And then I apply heat at 850 Fahrenheit. The tip of the heat gun is about half an inch above, it's really 5/8. I measured it. It's about 5/8 above the bolt in this picture. So you can see a time lapse of 32 seconds. It's just starting to show some melting. And then at 36 seconds, we've got melting going on. 45 seconds, a lot of flow, and the lasso ropes, if you will, have separated. And then within another 15 seconds or so, I spin that wooden board around and touch up any areas that are lacking solder. And this is just preparing the pipe cap so that I'm not doing this kind of thing when it's clamped to the PCB board. I want it already tinned. That's a word that most of us know. So this will keep solder from flowing on the inside of the pipe cap, and it just sticks to the outside, and you've got plenty there to flow to the PCB board when you get ready to stick it down to the PC board. I think you could use a lot less heat. I haven't experimented with that, but you figure it goes from in 10 seconds or 15 seconds, the whole thing is over. If you didn't have it nailed down through the bolt being tight, you wouldn't have time to mess with it being 13 seconds from start to finish. So if you take lower heat, it probably would be better to give you more, I guess, control. But there's nothing to do to me. You just nail it down and get it over with. It keeps me where I'm only working about an hour on a pipe cap. And when it comes time to put the pipe cap to the PC board, there's 6.5 dozen different ways to get that done. Here's a picture where I have C-clamped the pipe caps to a W1 gigahertz board. And I'm cleaning up the solder actually here, but I want to describe how this is sandwiched because it may be some non-intuitive things. First of all, these blue C-clamps have a piece of what do they call it? Asbestos type. It's not asbestos, but it's asbestos type material. And under each of the top of the clamps. And I just did that to try to keep the heat sinking property low because the heat's coming in from the bottom here. The The very lowest metal plate that you see is a hot plate. And it's just a little small, like 3x5 inch hot plate. I've got several different hot plates here. Some of them are more sophisticated and others are kind of basic like this one. And you can't control the heat on this guy. And it gets very hot, very, very, very hot. So I have the hot plate and then a 1/8 inch piece of sheet aluminum, and then the printed circuit board, and then the C clamps. The bottom of the C clamps are touching the bottom of the hot plate, and it's the hot plate that is clamped to a vise off to the left that you can't see. It's a good size vise, probably 10 pounds in weight. And this gets me where, as a fixture, it's all firmly assembled, and then I can just apply heat. And that's coming, like I said, it's coming up through the bottom. Now, I've never worried about other pipe caps that are on the printed circuit board. They don't come unsoldered, but if you were ever worried, one of the things I've learned that I can do through other applications is just use a wet paper towel and wrap it around. You still might get smoke, but it's probably not going to catch the shop on fire. And here is the complete, it's all done here. It's on the MBA board. Now, this is probably the main thing that I learned that I didn't know before. Hopefully, it's something that you can benefit by. But these pipe cap probe pins are soldered from the underside. And for 11 gigahertz, the probe length is critical. And this is what makes it work to me, is that we can use a 1/2 inch size and yet a very short and critical length probe that is inserted from the bottom and is perfectly straight and about as consistent as you're going to get as an amateur. So the green arrows point to everywhere that a pipe cap probe needs to be inserted on this board. And the pipe cap probes are shown over to the right. Now, I didn't even know this stuff existed, but I'm sure some of you did. These are actually in the category on Mauser of pin and receptacle. Pin and receptacle. These, of course, are the pins, but even the pins themselves come in variety of length, diameter, and head style and thickness. These are nail style, so they have a flat head and a certain diameter and a certain length, and the length is critical. So here's the data. The length is 0.179 inches, or 4.55 millimeters from the top of the nail head. The diameter is 0.018 inches, or 0.46 millimeter, which happens to fit a 0.022 inch hole in the PCB. And this company, Milmax, has a large variety of these, different lengths, different diameters, different nail style heads. But Mauser only carries a handful of all that Milmax offers. There is a minimum order quantity if you order directly from Milmax, but at Mauser, you can order one. So going back to the board, the pipe cap filter locations are indicated by these blue circles. So 3 of them. And then here's a picture of the, here on the left, the nail is actually inserted, or the pin. It's not soldered yet. And then on the right side, it shows what it looks like with it soldered. And there's the completed board. And this is the picture of it in the beacon. So working good, does everything that it's supposed to do, tuned up well, no problems. And that is all I have. Here are the references referred to earlier in the presentation. All these links would take you to these various places. Are there any questions or comments?
Hey, Jim.
Hi, Scott.
One of the things on the pipe cap pins. One thing I saw someone using was a hat pin, and you can get those off Amazon in copper, brass, silver. I think maybe even gold plate. Now, as far as the tolerances and lengths and diameters and stuff, it's kind of a luck of the draw, I guess. But those seem to work pretty well as well, also.
3/8" pipe cap ends are available at most plumbing supply places.
Jim, this is Don. I've just got a question. What about environmental effects? You know, temperature changes. In your experience, how sensitive are these pipe cap filters to temperature change?
The Q is too low. It's not an issue.
Well, that's a great question. I mean, if you talk about thermal and you look at those beacons, they're outdoors and they're going to go through quite a fluctuation of temperature. I think it would be a whole interesting investigation, you know, as to if there were enough time to understand what's going to happen over a couple of years' time as these beacons are exposed to the elements. But I'm glad that Kent can tell us that as far as the pipe cap filters, they're probably not going to change their filtration effect.
The Q is very low in those filters. They don't move far enough to change the bandwidth.
Of course, I've had a lot of concern about what's going to happen to other components. In fact, we made our beacon, the one that I've made anyway, to where it is remotely controlled, so that it can be, each element of the beacon can be turned on and off. Just because I thought it might be the best way to approach the heat problem that we have in Texas is let Al or Scott or, whoever's going to have a need to turn it on and off at will, and each part of it, so they can turn on the 10, you turn on the 24, they can turn on the 47, you turn off any one of those. And it starts with the GPS because that's actually got remote control. So we can shut it all down except for the receiver that's listening for the cell phone command. That would stay on all the time. I don't want to burn up the 47 gigahertz beacon when it gets to be 110 or 108. If we can just turn it on and listen to it for an hour and then turn it off, and then wait a few hours and turn it on and turn it off. But that might be overkill, and it might be that there won't be really any problem.
If you want to go higher, 3/8" pipe caps are available.
Thank you for that. I saw your chat. Any other questions?
I'll comment, Jim, on the earlier talk about the strip line. You were talking about the MATLAB. There are programs out there on Ubuntu or Linux that, like Octave, that's sort of a knockoff of MATLAB, and I've worked with those in the past doing strip line, trying to do strip line design. And you can find examples too with searches on the internet. And then the other issue is the board material that you work with. And our friend Kent here runs some boards occasionally, and he's offered a couple of times to run on special RF material, but you have to decide what material you're going to run on and use the proper characteristics for that material. And one other company that's out there for PCB that I've used, they offer I'll call it like a prototype board run, where you can build a board it's about 5 inches square, I think. And they have a particular RF material that they use, which is a Rogers material. And it gets kind of expensive. It's a few $100s to run something, but uh, it could be a situation where later on, if we can't get them run any other way, we could gang up boards that people want to run and put them on there, because most of these boards are not very big. Although with filter designs, if you're at a low frequency, they could get bigger. But we could,
Bob,
yeah.
I have large quantities of Arlon 25N, which is the same as Rogers 4350. That's in stock.
Okay. And so if we give you a board layout, how would that work?
I can mix it with some other boards and get a run made, and it'll be a lot less than what I just heard quoted.
Okay, well, good. That sounds interesting. We should be experimenting with that and trying to, because usually you don't get what you want until you've tweaked it 2 or 3 times at least to.
The challenge is some of those RF materials, you can't do plated through holes except through a plasma process that's horribly expensive.
So you have to use Z wires, I guess.
Not the preferred way of doing it.
What's the preferred way?
Pick a material which uses the FR4 type processing, which Arlon 25N, Rogers 4350 will do normal PC board processing, and you can do plate through holes. The Duroid materials, which has the dielectric constants near 2, it's hard to find a place that'll even touch it, because you're forced to use chemicals which will etch Teflon. And do you know what kind of chemicals are necessary to etch Teflon?
So the board material that you mentioned, is it plated? Can we do plated through holes in it?
Absolutely.
Okay. Because you notice there's a lot of free vias all around to get the ground planes tied together. So you need a lot of plated through holes.
Oh, I can't believe that. Let's just say the materials that will etch Teflon, the EPA does not approve of very highly.
Okay.
Yeah, Bob, I got 5,000 boards made last year, so the guys know me.
Well, I may come get some more information from you, and I've got a board that I've laid out that I can talk about in a little bit, and I may tweak the design to fit that material and talk you into running it for me.
What does it do, and what material did you design it around?
Like a Rogers, it's an odd material. I don't remember the exact number, but it's a laminate with a Rogers material on one side and FR4 in the middle is the way the manufacturer's data sheet read. But
Weird.
yeah,
what dielectric constant
the
did
problem
you
is the
design
Rogers
around?
material is so thin that they laminate it to FR4 just to give the board some strength so it won't curl, when you process it.
What thickness and what dielectric constant of the
I would have
RF?
to look that up. I don't remember. I just worked with the numbers that they said to use for trace widths and spaces, which is what you tweak in the long run here. I'll talk about it later when we talk about things that we're doing here, if that's okay with Jim.
Yes. All right. I'm going to move on here. This is going to be a replay of Al Ward talking to us about sun noise measurement. I can't see this enough, personally speaking, because it reminds me again and again and again. And so I'm going to start this going now. The important thing is that I've got the audio shared. So let's see if I've done this right. No, I don't think I have. Oh, shit. Sorry. I'm not hearing the audio being shared, so let me go back through this again.
Times these QSO attempts result in one-ways. And when you're on the microwave bands with similar setups, similar power, similar noise figure, and only one person is hearing one end of it, you start to ask yourself, well, what's wrong? And that's what we're going to talk about here. So go ahead to the next slide, Jim. So, most of the time it's, well, back in the old days, it's, can you hear me type of thing. And nowadays it's a lot of, can you see me type of thing, which is nice in that you do get DB reports. So it's nice to compare DB reports, from WSJT. But when you can't hear or see a guy, you first ask yourself, are you on the moon? And on the upper bands, you can get a little bit of moon noise. So that kind of helps to keep you on the moon. But then the question would be, okay, the moon's rising to the east. So when the sun rose earlier in the day, were you calibrated on the sun? And that's a lot of times that's what I do. I kind of hope that the sun comes up before the moon does, and you can use one to calibrate the other. Then the other thing is, well, can you hear your LNA noise increase when you power it up? Because most of the time, for an EME type of system, your LNA should be out at the feed, and you should be able to hear, the noise rising from that, and probably to the tune of 15 to 20 dB, depending on how much gain you have out there. So it's always nice to have a separate on-off switch for the LNA. You power up the transverter, then you power up the LNA. Oh yeah, I can see it. So there's a comfort level there. And I usually set the IF gain so I can get a nice S meter readings so that I can see that dB increase. I never set all my transverters down to S0 or S1 because then you don't know if they're broke or if they're working. So, we're not too worried about dynamic range around here, but the purists would say, you got to control that gain. But I take advantage of it here, and and use it to verify that I'm working correctly. So lastly, what is your termination of cold sky difference in dB? And when I asked that question to the Central States crowd, I was happy to see that a fair number of them had this sort of switch. And then, for those that don't, maybe they're asking what or why. So we'll talk about the advantage of having that switch and what it takes to incorporate that. Go ahead. All right. When you connect any antenna to a receiver, you're basically hearing or seeing noise that's displayed on your S meter. And if you hook up an HF antenna to an HF rig, generally you're going to see background noise, especially down on 160, 80, and 40. Maybe on 10 meters you might not, because it's generally a quieter band, but you will see some noise increase. And with the usual conversion gain that we have on EME, we still don't know if that's a good noise level or a bad noise level. What we need is a reference. And the best reference is to point the antenna down to the ground, which is actually 290 Kelvin. And then you point back to the cold sky. And the difference in dB provides an indication of how quiet or noisy your system is. And you always want the load to be higher than, we'll call it cold sky. And I'll show you why as we move on to a couple other graphs. But instead of pointing, well, back up, Jim. Instead of pointing the antenna down to the ground, I just switch in a 50 ohm termination for my 290 Kelvin reference. And because some of these rotors, like the new slew drives, they move so slow that to go from cold sky to ground, would take many, many minutes. So to have a switch where I can switch in 50 ohms right at the input to the LNA would be an advantage. And that would give you some confidence that your system was working or you had another problem. Go ahead, Jim. All right, in general, the background noise on the microwave bands can be as low as 25 or 50 Kelvin. And that's considerably lower than the 290 Kelvin from a load. Now on 6 meters, I think I remember, the sky noise can be like several thousand K. So it's very, very noisy. So the actual level depends on the side lobes of your antenna and what the other lobes are pointed at. And also the problem we have like on 902, 2304 is man-made interference from cell systems and from internet service providers. Bands like 10 gigahertz right now are pretty quiet. 3400 is maybe. 5760 is pretty noisy, and 2304 is getting there, and 902 is really noisy. When I say noisy, I'm talking about a lot of man-made interference. I mean, years ago when we first got on EME, we didn't have these issues, but we didn't have fast internet either. So I'm blaming it on the fast internet that most of you guys out there have, maybe not me. So let's move on to the next one, Jim. All right, so first off, when we're dealing with sky temperature, we need to be dealing in kelvins. And it's not degrees Kelvin, it's just kelvins. And you can convert the noise figure to a temperature by taking the noise figure in as a ratio, subtracting 1 times 290 Kelvin gives you 35 Kelvin. So a 1 dB, or excuse me, a half a dB noise figure converted to kelvins is 35.4. If you go to the next slide, because where I have a graph of that. And okay. So here's a graph of that. Basically 0 dB noise figure is 0 Kelvin. 2 dB noise figure is about 170 Kelvin. And in between, you get the numbers like half a dB. Down on the x-axis, you go up to the curve and over, you get that 35 Kelvin. For a 1 dB noise figure, it's about 75 Kelvin. And we need to convert dBs to Kelvin so we can add on antenna temperature to it. Go ahead, Jim. All right. Can you slide it up a little bit, or do I do that here? Cut off a little bit there. All right. So there we go. So if we install our 50 ohm load on our LNA, our equivalent system noise temperature will be the 290 Kelvin of the termination and the 35 Kelvin of the receiver for our half a dB noise figure receiver. So that equals 325 Kelvin. Now, when we attach the antenna to the input of the LNA, our equivalent noise temperature is now 50K plus 35 equals 85K. Well, the nice thing about these two numbers is you can take 10 log the ratio of 325 divided by 85 and take 10 log of it, and you get 6 dB. This is a good number to try to achieve on any microwave band, where hopefully your antenna temperature is lower, and that takes a good antenna, and it takes a quiet background, if you will. We can go, let's see. If we don't see anything like this, then we probably do have an issue that's worth looking at. Go on there, Jim. All right, here's a plot that's kind of interesting in that it shows the sensitivity versus noise figure. This is a pretty basic equation that says the sensitivity is minus 174 dBm per hertz bandwidth plus 10 log bandwidth plus 10 log noise figure. And if you had a perfect receiver in a 1 hertz bandwidth and 0 dB noise figure, we'd have a noise floor of minus 174 dBm. And if you look over here at this number, if your termination is 290 Kelvin, then this TA over T naught subtracts out, and you have just noise figure. So you have a straight line of 0 dB noise figure is minus 174 dBm. If you go up to 5 dB noise figure, it's minus 169 dBm. This is in the system where the termination resistor is 290 Kelvin. But in the world of looking up at the sky, we get to manipulate this last term out here and look at the effect that lower antenna temperature has. So if we have a 25 Kelvin noise temperature for the antenna, a 5 dB noise figure, still provides maybe an extra dB or so of sensitivity. But as you get down closer to 0 on this blue curve, you can see that the sensitivity is improved immensely with lower noise figure, but also lower antenna temperature. You could generate another plot here of, say, TA equals 10 degrees, and you're going to be somewhere down here as well. And you can also see if your sky temperature is more than 290 Kelvin, you're up here where noise figure doesn't make a lot of difference because you're totally dominated by the antenna temperature. But in microwave situations or installations, we'd like to be in this range here where you can actually get maybe a 7 dB or even greater 50 ohm over cold sky. I'll go on there, Jim. All right, so the next two slides show a couple of ways of incorporating this cold sky determination switch. And if you go to the next one, it's basically a block diagram of a transverter system driven by a sequencer. So you'll probably get some other ideas here, hopefully, but these are what typically my system would look like in terms of the transverter hookup. You've got an IF rig. A lot of times you have a transmit and receive line going to a transverter. And then on the transmit side, we're going to send power out to the PA, and then we go to our, we'll call it our septum feed, which is typically used on microwave bands. And this septum feed is for generating circular polarity, which we do on all the microwave bands from 902 through 10 gig right now. Or excuse me, not 902 through 5760. 10 gig is linear as well as everything above 10 gig polarity. On receive, I have a relay in front of the LNA. And you can see that connected to the receive port. I know you can't see my cursor, but hopefully you can follow the arrows from the septum feed. Oh, thank you, Jim. It goes into a single pole double throw relay to the LNA with a 50 ohm load on one port and the antenna on the other port. And it's this relay here that we're going to control to look at, we'll call it cold sky over 50 ohms. Now, just to talk a little bit about a sequencer here. This is your typical DEMI or W6PQL sense sequencer. Normally, there's 4 outputs, and these can be configured in various ways. The normal receive state is in the number 1 position. So I'm sending 12 volts to my LNA. And then these other number 2, 3, and 4, number 2 is 24 volts on transmit. Number 3 is control line. And number 4 is a transverter control. You can do this in various ways, but basically I'd like to make sure that my relay is terminating the LNA before I go to transmit. So the main purpose of a sequencer is to help control the PA. Now I realize I was talking to, I think it was Jim earlier, and I think one of the ICOM rigs, or maybe all the ICOM rigs, have some sequencing both going to transmit and back to receive. And sequencing going back to receive is as important as going to transmit. Basically, you want to limit any power going out until your system is in the transmit state totally. And when you're working with waveguide relays, you've got maybe 100, 200, 300 milliseconds of time as it transitions from receive to transmit and from transmit back to receive. So the TR sequencer here sequences going to transmit and sequences when going back to receive, which is very important. Now the next thing is how do you control this relay out here? Well, the way it's set up right now is if I want to go to a termination, I supply 12 volts to this relay through diode D3. Normally, the control voltage comes through D2. And of course, putting a diode across the relay coil is a good way to keep you from getting jolted, and also protecting other components and circuitry. So I always put a back EMF diode across a relay coil, that is. So when I go to termination, I just supply 12 volts or 24 volts to D3. And this guy will go from antenna to 50 ohms. And that way you can easily get a quick check, a quick sanity check as to how your system is working. This is not a fail-safe situation. I don't use this particular method unless my relay, like I have one waveguide relay on 10 gigahertz, it normally stays in the receive mode until I go to transmit because it pulls a lot of current. And the current, it's not a, it's a fail-safe type of relay. So I prefer option 2 here. And if you just flip to the next slide, this particular slide here, when the system is not fired up at all, you can see that the relay, normally closed position, is to the 50 ohm load. So when this whole system is off and when I'm not energized, the LNA is terminated. So I only go to the feed through the normally open port when I'm actually receiving. And that way, when I want to go to termination, I just remove the 12 or the 24 volts from the relay. So that's what this switch is doing right here. So it's another way to do it. It all depends on whether or not you want to have this relay connected to the LNA energized when you receive or energized when you transmit. Personal preference. I like this method better than the other one. Any questions about that? All right, let's go on, Jim. Now we need to move on to how we can make that measurement. So let's look at several methods here. This is the old-fashioned way of doing it with the GR meters. I like these. They have pretty good averaging. They work at 30 megahertz. We convert them to 28, and they have a nice big scale. And there are other ways of doing this, but these are ones that I've had around for years. And so this is what I'm kind of used to using. And you can see, especially on the meter on the right, you can see it's 10 dB full scale, and when you're down 10 dB, you're over here. So you got a nice range of you have a nice scale, if you will, for looking at how many dB increase you have either in moon noise, sky noise, sun noise. Just very universal. Go ahead, Jim. Excuse me. This is the system that I use predominantly out when we're doing portable measurements for sun and moon noise, and it converts the 144 megahertz down to 28 for the meter. And I got a little preamp up here as well for lower gain systems, because this noise figure, or this meter, has a pretty high noise figure. It's not like your weak signal receiver. I mean, a noise figure is it's got tubes in there, so it's probably at least 10 dB. So you at least need enough noise to overcome it. Otherwise, you're going to be sitting down here and on the far left-hand side of the scale and not be able to make any meaningful measurements. Go ahead, Jim. This is probably my first method that I used years ago, and it works well, but it's kind of a narrow band approach, if you will. You basically take the audio out of your speaker, headphone jack, or whatever, and you put it into an AC voltmeter like this, and you get a nice dB scale up there, just like the previous measuring instruments. But in order to make this work, you have to turn the volume up on your radio to get a reading, and reduce the RF gain to get it down in the linear range. And most of the time, you should probably turn the AGC off. So start with that, increase the audio gain, turn the AGC off, and turn the audio up, and reduce RF gain. And you can generally tell if you're getting meaningful numbers by adding an attenuator in the RF line, or some sort of self-calibrating. But you have to get this meter, you have to get your whole receiver operating in the linear range. The disadvantage of the audio meter is that it does operate only over several kilohertz. So it's going to give you kind of a jumpy reading, but you can put a capacitor across the input and kind of squelch that a little bit. But I also use this on 5760 at times, because the GR meter is picking up so much broadband noise, man-made noise, mainly ISPs and such, that it's really hard to make a meaningful measurement. So I crank up the audio meter and or look at it on my flex radio, if you will, to try to get a noise measurement over a narrow band. But it's another technique. If we go on to the next one, I'd never tried this until I was talking to K0 DSP, I don't know, a month or two ago, but it's using the echo mode on WSJT. And this is explained in detail on Bob Atkins' website. He's got a plethora of good stuff. So check out this URL, bobatkins.com/radio, and you'll see this, or you'll see his instructions on how to use WSJTX for measuring noise. And what I did was, you'll see this better on the next slide. In fact, why don't we just go over? This is on 2304 that I'm making this measurement, looking up at the sky. And you look at these numbers here, this is basically, I'm getting like a 60 dB level. And then when I go to cold sky, it drops down to 54 dB. So the difference between these two is approximately a 6 dB termination over cold sky noise. And so this is pretty good for that. It would be, well, what am I trying to say? It would be, it give you a good rough measurement if you have a problem or not. I don't know that you could ever get down to tenths of dBs, but I don't think we're interested in that. We'd like to know probably within a dB or so of what our termination of cold sky noise is, just for a reference for us and our system. And if you had a good number today and you're able to work people, and in a week or so, you still had a same good number, but you can't work people, then it tells you probably have some other issues. But at least it tells you that you have a system that's capable of seeing signals, on the moon. Go ahead, Jim. So what are some of the solutions? A lot of times we need a fairly good high gain preamp out at the dish, only to overcome line loss, if you will. But that also does not help the intermod. So the intermod is really these 2x1 products that are introduced when you take two signals and you mix them together, and they provide an in-band response that you really don't want. So a lot of times what it takes is to add a good filter after the first stage, and also consider SAW filters in between L and A gain stages. And item number 2 is what the guys like Tommy Henderson do, WD5AGO and his preamps, and also the Demi preamps. I had a nice Demi preamp on 902. It's a 2-stager, and it had a SAW filter in between the 2 stages. And fortunately, even though we're being invaded on our bands, that does allow us to buy or find SAW filters, surface acoustical wave filters, that are actually designed for some of the bands that we operate in, like 902, 2304, and 5760. I'm not sure. I don't think they're readily available up there, but I might be wrong. The other thing is to put a good surplus cavity filter in between the preamp and the transverter. And they are available for 900, 2300, and 5700 bands. There's some for 10 gig also, but I haven't had a need for that. If we go on to the next one, Jim. This is the filter that I had to use on 902 at home. I could not operate the 902 band terrestrially unless I had this bandpass filter on the front end of my transmitter, or the whole rig. Actually, I transmit through it as well. But, these, let's see, the loss is like 0.9 dB. So that limits my noise figure to about a dB over the transverter. But it's either that or not work people. And when I'm on the moon, I still have this filter in line between the preamp out the antenna and the transverter. So these are, some things that you may have to do if you're trying to stretch the noise floor down, if you will. Go ahead, Jim. This was a little 2 gig filter that I tuned up here for 2304. It's a nice little guy. It's got 1.3 dB of loss, and it's 60 dB down at 2100 and 2480. So this, you can see here, this is a plot from 1 to 3 gigahertz. So 1 gigahertz down at the left side, 2 gigahertz in the middle, 2.3 gigahertz here, and 3 up here. And we get rid of all the PCS cellular stuff on either side of it. So these are things that you sometimes have to do. In fact, actually on 2304 at home, I have a filter. Most of these I've gotten from Kent over the years. It's a big filter, but it's on the front end of my whole system. And I had to do this because when I aim at 30 degrees towards Chicago, I'm looking through that cell tower. And Jim, this is the cell tower that you were interrogating there just northeast of me. So I finally decided I'm just going to stick the filter in and I'm going to live with it. And, you know, as proof, it worked Florida the other day. So sometimes you just got to do what you got to do and suffer the consequences of a little bit less in the sensitivity area. But when you got a noise source that's 20, 30 dB over the noise, you know, you can make a choice on that.
Can I ask a question about that filter?
Yes, sir.
Did you change the screws on it to those longer screws? And then which way do you tune it when you start tuning on it? In the middle, out, or on the ends?
Well, that's a good question. It was a long time ago when I did this, but that certainly looks like non-plated brass screws. So I'm guessing that I probably needed more insertion than it was originally designed for. So I'm probably bringing this filter down in frequency, Bob.
Okay.
Yeah. Yeah, those aren't original, are they?
I just noticed that. I was just curious.
Yeah. Yep. Yeah, it probably was tuned to higher frequency. Okay, go ahead, Jim. So, in summary on this one here, incorporating a termination of cold sky switch will help the EME operator establish a norm for their system. When I get on the moon, I'm always checking this on, I'd say, well, all my systems. I always have some way of comparing termination to cold sky. And, you know, it's been real beneficial there. Any questions? All right, well, let's go on to the second one. It's kind of kind of an extension of this one. I think you don't think he, okay, another, okay. Trying to think of what the, let's see, what's the name of it? Yeah, okay, that's it. Yeah, I originally presented this back in 2012, and in 2024, we had some numbers, some updated sun noise numbers. I think we obtained these out at Bob Stricklin's place when we were out there during the eclipse. In fact, I'm pretty sure that's when it was, February 3rd of 24. And I'm representing it here because I've seen some discussion on MoonNet about comparing dishes based on sun noise. And of course, that's, you know, that's two operators, two different antennas, two different receivers, you know, all sorts of differences, if you will. And what I did here was we've used the same receiver for all dishes, so it was easy to make a comparison. But it brings to light some things having to do with sun noise at low numbers that I wanted to present. So let's just go ahead. We can skip that one there because that's just the same noise meter slide. Skip that one. And this one because we had talked about it. All right, here we go. The question is how do we compare sun noise readings? Well, you know, if Bob was getting 20 dB of sun noise and Al's getting 30 dB, you probably say, well, Al's system is 10 dB better than the other guys. And for anything over 20 dB, that's probably true. But when you're making a sun noise measurement in dB, you're really looking at signal plus noise over noise. That's what you're comparing. You're off the sun, so you're measuring noise. When you go back onto the sun, you're measuring signal plus noise. So when you take a look at this, signal plus noise to noise, if you break it out, it's really signal over noise plus noise over noise, which is 1. So therefore, signal to noise ratio, which is what we should be comparing, is signal plus noise to noise minus 1. So keep in mind, signal plus noise to noise is what you measure when you're looking at the sun. When you want to compare readings, you really need to be comparing signal to noise ratios. If you go down to this table here, you can see that 20 dB of, we'll call it sun noise, is real close to 19.96 signal to noise ratio. You get down to 10 dB, it's still pretty close, 9.54. But as you get down to, let's stop off here at 3 dB. If you're measuring 3 dB of sun noise, that's 0 dB signal to noise. That's because if you had 3 dB of sun noise, that meant that you had 3 dB of noise and another 3 dB of sun plus noise to noise. And in reality, they're the same level. The actual level of the sun is the same as the noise, I guess is a better way of saying that. So actually 3 dB of sun noise means that the sun noise is equivalent to the noise level behind it. So the actual signal to noise ratio is 0 dB. They're the same. It's unity. And they do add, because powers do add. Just like if you had two 1 watt signals and you added them together, no losses, you're going to get 2 watts or 3 dB more. And if you're only getting, say, 1 dB of sun noise, that's actually a minus 5.87 dB signal to noise ratio. So you really need to compare signal to noise ratios and not signal plus noise to noise ratios. And you can see that from that table. We'll go into some examples. Go to the next one. Here is a graph of that same curve. Basically at 20 dB or so, they're about equal. 10, they're pretty close. 0 dB signal to noise ratio, that's like 3 dB of sun noise. And you get down here, if you're only measuring 1 dB of sun noise, that's only what, minus 5 dB or so signal to noise ratio. We'll move on to the next one, Jim. Here's just a couple of comparisons, or a couple of examples, if you will. If station A is measuring 20 dB of sun noise and station B is measuring only 10, then converting them back to signal to noise ratio, you get 10.42 dB, or a change in sensitivity of 10.4 dB. Now, if you're comparing station C, who is receiving 10 dB of sun noise, to comparing to station D, who's receiving only 3 dB of sun noise, the difference there is nearly 10 dB for a 7 dB drop in sun noise. All right, moving on. This is just an expanded scale, so we can move on from here. Now, if you actually want to go through the math, this is basically what we're doing. If sun noise from antenna 1 was 2 dB and 4 dB for antenna 2, this is how we'd make the comparison. You take the 2 dB, you got to convert it back to a ratio. So you divide by 10, take the inverse log, subtract 1, 0.585, 10 log of that, minus 2.33 dB. So it's pretty simple in terms of the math if you got a little scientific calculator. And the same with 4 dB. You divide 4 dB by 10, inverse log, minus 1, and then you get a factor, a ratio. You convert it to dB, and you get 1.8 dB, and you just subtract the 2. And antenna 1 is basically receiving 4 dB better than antenna 2. Pretty simple math, but you got to realize this is what you have to do when you have small dB numbers. Go ahead, Jim. All right, this is these are some measurements that we made back in May of 01. They're at 24 gigahertz, and hopefully they'll kind of send a point home a little bit here. It's the same noise figure, 2.4 dB, and this was connected to each one of these antennas. And you can see the antenna listed over on the left. And on a 12-inch commercial dish, measured 1.5 dB of sun noise, converting it to signal to noise is minus 3.84. And we're going to say that this is our reference, if you will. And this is a theoretical gain. And based on that, this is going to be our reference. So we're going to refer everything to the sun noise that we made with this antenna. So basically, if you double the aperture, which is what we did here, we're receiving 4.2 dB of sun noise. You convert it to signal to noise ratio, and then you compare them. The difference is nearly 6 dB. That's exactly what it's supposed to be. You double the aperture, you're going to gain 6 dB, even though you only gained, well, let's see, you went from 1.5 to 4.2 dB of sun noise. But in reality, that's almost 6 dB of gain. And that's exactly where you want to be. And we looked at some other ones here, like a PCOM dish. And it's close, but not as good as the MACOM dish. And Joel had brought his stuff down at the time, and we were looking at it. And we made some comparisons. And his dual band 10 and 24 gig feed on a 2-foot dish came in at 5.64 gain over the 12-inch commercial, pretty close to the 24-inch MACOM, specifically designed for 24 gigahertz. So the dual band feed actually works pretty well. And then we had a 55-inch dish here, and of course it beat everything out, but it's actually a bigger dish. But when you look at these numbers right here, it kind of gives you the idea or the impression that these numbers kind of make sense now, even though the sun noise maybe threw you for a loop, because you would have thought double the aperture, I should go from 1.5 dB to 6 dB of sun noise. But in reality, it's only 4.2 dB. But that's all you could expect on sun noise. But in reality, it's the 6 dB difference that you're looking at due to the aperture. Every time you double your aperture, your gain goes up by 6 dB. All right, let's move on to the next one here, and I think that should be about it. We did some very similar numbers. Of course, these are the older numbers. Probably don't. Yeah, these probably don't tell the story as well as the other ones do. Mainly because we're looking at we're looking at antennas here that are all about the same size, but you get some idea. The sun noise, 1.5 dB with a 24-inch dish, 1.3 with a 30-inch, 1.1 with a 24, and even 0.22 with a little offset fed dish. And when converting them back to signal noise ratio, then you look at the difference in the gain. So it looks like, yeah, you might say that the 30-inch dish I had here was not as good as the 24-inch dish. So this is the right way to make comparisons with sun noise, converting them back to signal to noise ratio, and then look at the relative dBs. And I always put this down for reference because we weren't measuring gain. We were just trying to get some difference, an idea of the difference in performance of the various antennas and make comparisons. I think that's all for that, Jim. Can't remember what was after this one. Yeah, moving forward, I think Jim and I want to do some tests at 47 and 122 gigahertz. So I think stand by for those events to happen. Especially would like to do 47 and 122 because those are two bands that we're kind of highly motivated to work on at the moment. Any questions on anything?
I have questions and comments.
Yes.
What about, so when you were making these measurements, you're using the same receiving system and the same frequency to make or compare all the different antennas.
Right.
Otherwise, wouldn't bandwidth and variations in the equipment that you're using make differences too?
Yeah, this is just all hooking up I think we're using like a 1 meter cable from the transverter to each antenna.
Okay, and then the other thing is the situation about how well the dish is illuminated could play a role here too, right? How good your feed is coupled with your dish.
Correct. And we were making some adjustments based on the sun noise numbers that we were getting from what I remember.
So you would get them reading and then you would try to tune it up while you were doing it to make it more like what you thought it should be, I guess.
Except during the solar event.
Right. Okay.
Did we lose him?
Any other questions or comments from anybody? Well, hopefully I didn't bore you to death, but you can, I think Jim's got them up on the on our website, or we'll have them up there shortly. I know the first one is.
Okay, I've stopped that video. Bob, do you have any other comments on that presentation?
Oh, I enjoyed listening to it again, just like you said. I can listen to Al over and over again and still learn from him. And then, I'm sitting here thinking about the same things I thought about last time, though, too. It makes me want to get busy and get equipment working and go make my own measurements. And some of the stuff I can talk about later is related to astronomy. And I participate in an astronomy group, and those guys are out there doing the same things, trying to figure out how to make a dish work better and look at noise and things like that. So this is sort of a universal problem people have.
Bob, if you wouldn't mind, why don't you go into what you have to say here
Okay.
and show us what you've got? I think that's more timely than replaying another stored video.
Okay, sure. Let me share my screen here. I'm going to try sharing my desktop, see if that.
Take your time. I see the desktop.
Good. So it's funny, but some of the things I've been working on sort of dovetail with what's being talked about today. What I need to do is make sure that I have this as big as I can make it and centered as well as I can.
Can you make it fill the full screen?
Yeah.
That's better.
It sort of wants to jump around on me. I don't understand that exactly. But what I'm doing is related to the astronomy side of things. The guys there, there's one fella in particular that's spent a lot of time developing some software that analyzes data that you're receiving with your dish. And he was lamenting the fact that he wanted to be able to switch back and forth to a 50 ohm reference, just like Al was talking about earlier. And so I proceeded to design this circuit that essentially takes an input from a dish or an antenna, and then it has a filter on the front end. And I picked this particular filter, which is a 1.420 gig filter to get the H1 signal in astronomy. And then I'm feeding that into this switch here that will switch between a 50 ohm resistor and an LNA. And so, there was a fellow named Fritz Dickey that did this in astronomy back in the 50s, where he was switching back and forth. And that's essentially what this is going to do, is to switch back and forth to a reference. And in astronomy, you're trying to determine the difference in a signal, which is it's really like a carrier or similar to a carrier at a particular frequency, and noise in your system, and RFI that may be at play in your area. And it's the same with microwave operation. But I've got this set up with a power supply, which let me see if I can go into this sheet here. I wanted to include what I'll call a low noise power supply. So most of the time the guys in astronomy are trying to power their things from like a USB plug or a computer that they happen to have with them, and they end up with a lot of noise from switching noise and things like that. So I've included this quietening system or a system to try to remove all of that to get the purest 5-volt level signal that I can. And the second part of this schematic is that the power coming into it, the voltage is going to come in down the coax feed line, and it's going to jump between 6 volts and 7 volts. And so I've got this detector circuit here to watch that voltage, and when it makes the transition, it's going to provide the control voltage needed on that previous slide to make that switch go to the 50 ohm load. Uh, Now, when you do these things, hams or people involved all have different ideas about the way they want to approach them. So I try to make something work for multiple people. And I've included this circuit here, which is just a relay to give you a dry contact here that you could do something else with externally while monitoring this incoming voltage. And so, and that something else might be this. I put in this preamplifier here partially because that you mentioned a filter from NOALAC earlier. The NOALAC people make a preamplifier and a filter that's useful for radio astronomy, but you can't get them right now for whatever reason. They haven't been able to supply them. So I thought, okay, well, this would cover all of those needs. But this LNA is where I get into the issue about the RF PC board needing to be uh, designed a little bit differently. And before I go to that, I'm going to tell you about this other box over here, which is this box is the remote box that I've designed to be operated by like a Raspberry Pi, like a Pi Zero, which is, a $15 computer at Micro Center. And if I have this set up on a hat board, they call it, so it'll plug right into that guy. Then I've got a stepping type of a regulator here that will produce that 6 volts and 7 volts, depending on what you do with the reference. I've just put a device here to switch the reference levels so that it'll pump out either 6 volts or 7 volts out there to the device. Okay, so now what I'm doing with this stuff is I'm building actually 4 different PC boards. And so the uh, the regulator stuff and the hat for the Pi would be all on just an FR4 board. But this filter circuit and this preamplifier would be on ideally on a RF material board. And so if I shrink this down and I open this sheet, you can see my board layouts here. I forgot I had all of these. I also have included a shield board. And so what I've done is sort of what it's funny, Jim mentioned earlier about Milmax. I've set this up to take some pins that will fit right in these holes in this board. And then the top level board, which will be this board, will have a pin that has an 18 thousandths diameter pin sticking out. So these will just sandwich together and all plug together. And then the RF line here is providing the input to the power board. So it's tapped off of that RF signal. And then this big long block here is the filter, which I've designed this with a filter from Mini Circuits, but Mini Circuits has multiple filter types you can pick from. And the one that I've thrown in here is a zero point 0.9 dB loss filter. And there is another one that they have. This filter here is about a $70 filter. There's another one they offer that's, I don't know, $7 or $8 that has a 2 dB loss. So I've got another board that's not in this collection here to support that other filter also. And so then it will get to be a situation of what do you do as a user? Are you willing to spend the extra money to save a dB or two? And in astronomy, that's going to mean the difference of can you pick up a signal that you couldn't pick up otherwise. And people are not just looking at the H1 level in the Milky Way, they're also trying to look at galaxies and integrating over long periods of time. But I got into some interesting things too with KiCad. First of all, I'm on the bleeding edge here. I'm using 9.99, which I started using some time ago. And what that is it's like the developer's version where they roll out a new version every night or two. But they had some features in it that I really just felt like I had to have, and I upgraded. And then after I did upgrade, I found out you couldn't go back. The only way you can go back is if they do a really major upgrade, and then I can finally get out of the leading edge. But I wanted to lay this out as a sort of a strip line design and some of the critical RF stuff. And to do it, to get the proper impedance, you needed to be running like a trace width of 18 thousandths of an inch. And then you come down to the device package for the LNA, and it's got smaller width pads. So ideally what you would do is have a tapered connection there between those traces. And the only way you can do that really is to go into KiCad and change the individual geometry of each one of these connections. And I'm heavily using Chat GPT now. It's become my buddy that's with me all the time, it feels like, when I'm working on projects. And Chat GPT laid all this out for me, laid out these little tapers. I handed Chat GPT this PC board layout with all the lines in it and told it I wanted these tapers in there, and it did it for me and handed me back the board layout. Now, I make that sound like it was real easy, but it probably took 1 or 2 days, maybe 3 days, working back and forth to finally get that working properly. But and then all of this stuff on the top stays the same to go to a second board and drop in that other filter. Let's see. And then down here below, this is a board just to do the DC injection. So coming off of this Raspberry Pi board will be that voltage, and I've just got this set up to put a wire in here essentially with a couple of SMA connectors on it to get the power into that line. And once again, you get into what you'd like to have is an ideal impedance match between this to not cause a bump in impedance here. And so I decided to just experiment with different line widths and see what it looked like. And the ideal line over here at FR4 is 60 thousandths thick. It's something like 3 millimeters wide. So even this one is not going to be as wide as it should be to get the best match. Now that match can vary. Kent asked me earlier what kind of dielectric constant that material has. It has a dielectric constant of 3.38. And he said he had some 4350 that has a dielectric constant of 3.48. And so then the next question is what thickness is the material that he has available or that he uses. because that's the other piece of this. It will affect that equation for what those lines and spaces need to be. So that's pretty much what I was going to talk about. The let's see. And like I said, my approach, I use this 4 PCB, and I have this PC board I'm holding up on my video side over here at 6 by 10 inch, and I put multiple projects on this board so that I get 6 or 8 different designs at once. So I get in this mode where I'm trying to complete all my designs, and then I just in KiCad I paste all these together and make it look like a 6 by 10 inch board. And then I have a shear that I bought from Harbor Freight that when I get the board in, I can shear them down into individual boards. And then I spend a month or two probably testing and debugging these things, trying to find out, what was wrong. And I make mistakes and I fix the PC board and go back out and do it again on another build at a later time. So with that, I'll stop talking and answer any questions or take any comments.
Bob, this is Ben, K4QF.
Yes, sir.
Is that Dickey the same guy that developed the Dickey fix for radar systems?
It probably is. I'm not familiar with what you're saying for sure, but it probably is.
Okay, thank you.
I have a book on radar, the development of radar. I could look in there and send you a note later and let you know, Ben.
I was
Bob,
working.
Ben, I'm sorry, this is Don, V6HQ. The answer is yes. Dickey was, one of the pioneers of radio astronomy, and that switching system, that he developed was primarily focused on trying to take gain variations of the amplifiers when they were measuring different astronomy targets or sources. And so switching back between a constant, you know, source, this 290 degrees nominal temperature, and then the sky temperature, let them take out their amplifier gain fluctuations over their observation time. And so it was just a real milestone in radio astronomy. Sorry, Bob, for that divergence there.
No, that's wonderful. Yeah, the interesting thing is that the progress of radio astronomy has been all about how to separate what's really a signal from noise. And it's the same in weak signal work. You're trying to find out how you can get the best performance you can out of your rig. And the other interesting thing that I've learned going forward in radio astronomy is that, like when Dickey was working in the 50s, he had a certain amount of problems with RFI and other things, and all those problems have progressed as time has gone on. Now we've got satellites to contend with that are getting to be a bigger and bigger issue, but they've also moved up in frequency where a lot of work is done today in the up to 250, 240, 250 gig. And they have different, essentially what they're doing is looking at the chemistry of atoms in space that happen to emit spectral lines at different frequencies. And so uh, the capability of radio astronomy is continuing to improve today even because of that.
Yeah, 30 years ago, I was working with Sandia on a missile detector radar, and they incorporated a Dickey fix into the radar, and I had never heard of it. That's the first and probably the only time I've ever heard of the Dickey fix for radar systems.
That's all I have, I guess. If you want to go ahead, Jim.
Thank you, Bob. I assume that you could probably put something together every single month to keep us is kind of in track with what you're doing over there.
Sure.
You're certainly one of the more active developers of different things that have application with what the rest of us are doing. So we'll come back to the agenda and just finish out here because I think it's getting late. And do we have any other show and tell from any other members? Okay, let's just go through how the calendar looks. I heard that we might see some Leonids meteors tonight, and that is the next thing that happens is this annual meteor shower. Next weekend, there's a couple of us that are planning to get out and check out some locations north of North Dallas. I put the locations in here. And then as we get to the end of December, we've got a couple of other locations that we want to do a checkout on. We welcome anyone that wants to ride along and just do the observation. Anyway, these are some locations that would probably produce 24 and 47 gigahertz contacts, 10 gigahertz certainly, but at the 31st, which is the end of the year, that's the last day for the 47 gigahertz DX cumulative contest. So any locations we haven't activated, we want to have them done by then so that we can turn those results in. In January, we're planning a MAD day at the 3rd, and then another Zoom meeting on the 10th. I would solicit your presentations. 16th and 17th is the annual Cowtown Hamfest. There will be presentations from the club put on there. Usually it will consist of Kent, the W5VJB, and myself, possibly others that will just go through the how to get started in 10 gigahertz or on microwave. And then, of course, it's a great hamfest. The VHF contest is on the 17th through the 19th. I put the winter field day on here. I got to turn down the volume on my headset. And I did this because I had some inquiries as to if there would be low and mid microwave activity on that day. And I don't think it's been on many of our calendars before now, but there are some groups to the south of us that are going to come within DFW range. And so might be some more to come on this as we get into January, where we could help support these rovers that are in. They're going to run 1296, 2304. These are our perpetual items. I'll let you read through that list. We read them out routinely, but the main one is the NTMS lunch. every Tuesday, 11:30 a.m. at Texas Smokehouse Barbecue in Richardson. And probably call out the Hoot Owl Net. That is going to be another one tonight on 50.125, called by Al, W5RLG. For old business, there is a beacon party planned for Christmas week. I don't think those folks are online today. But I know that Al and Wes had spoke up at the last meeting about this party that would travel to Denton and work on the beacons there. Next item is a micro grant from Irving Club, and that has been in progress. I listed this under new business. We made an application to Zoom to lower our rate based on our nonprofit organization status, and they denied that. I plan to reapply. I don't know the criteria that we need to meet, although initially it was just nonprofit status, and yet they denied us to lower our rate. That's one of our, I think it's the second highest thing that we pay for, and it would be good if they would lower our rate. Society membership dues are due. We're at the end of the year. I'm working to try to send an email that will actually have the link to the PayPal switch, so that you can just simply click on the link in the email to renew your dues. I have asked Wes for a list of paid members and donors so I can compile that for January. Is there any other old business or new business to discuss?
Jim, I have one other comment.
Ben.
From the microwave update activity, and this had never occurred to me, that people could work on a VUCC from a portable location. I always tried to get VUCC from home, which I finally did on 10 gigahertz, but I thought if you can do it from a portable location, maybe I should go back and look at portable locations. So there's a mountain north of Oak Ridge, Tennessee, about 10 miles, named Windrock Mountain. And it is 18 miles from a four-corner grid corner in Knoxville, Tennessee, line of sight. So I thought, where's the next fifth grid for that? And so I looked at the Covenant College on Lookout Mountain, just south of Chattanooga, Tennessee, that's in the next grid, and it is 99 miles, but it is strictly line of sight between Windrock Mountain and Lookout Mountain south of Chattanooga. So we're getting ready to try to organize a VUCC party somewhere. And then I took a look at Cheehaw Mountain in Alabama, which is 2,400 feet, and it's about 38 or 40 miles from a grid corner in Gadsden, Alabama, and again, line of sight. So then I looked south of Cheehaw Mountain to see where the fifth grid would be, and that's about 38 or 40 miles south, and again, line of sight. So I'm hoping that we can hang some more wallpaper for our operators in this area.
That sounds like a lot of homework, Ben, and I appreciate that because I've done the same thing. And I sent out an email soliciting for volunteers or participants that would be willing to go west to the Lincoln National Forest. I got one response, and I've had to visit with somebody last week that said they were interested. So there's three of us that would go to the west. And I've already been out there and inspected it myself. And there is a 10,000 foot high mountain location that has a vista to 5 grid locations. So there's a magic 4 corner location, and then there's the fifth grid that's about 60 miles away, but line of sight. So I'm doing the same homework on my side, looking to gather some NTMS folks that would go out to the west and be prepared, probably with 10 and 24, maybe 47 gigahertz, and get VUCC. Would you keep us in touch with what you're doing out there to the east from us? I think Ben went away, but anyway, I'm sure he will jump back in there. But that would be interesting to see what they're doing to the east on a VUCC for microwave bands.
Jim, I can show you one more thing real quick if you like.
Yeah, go ahead. Go ahead.
Let's see. I operate these Meteor cameras here locally also, and there is a thing out there called Global Meteor Network, which you can get this page I'm looking at if you just do a GMN space status, and it shows you the meteor activity that you can look at daily. And my cameras here in North Texas are listed in here under the Texas cameras, for instance. And if you click on these screens, you get different sort of results. But this shows you how many meteors that were present here at my location last night. Where the ones with that look like dotted lines, those are not meteors, those are airplanes. But there is some AI software that sorts out all the airplane traffic that went over. And then the arcs are the stars. But every one of these lines like this is a meteor coming through. And if you play around with this web page a little bit, you can go down to the bottom and it shows you the different meteor showers and what the activity is. So if you want to have a feel for like time of day or what your possibility is of getting meteor scatter, then this is a good place to go look at it.
Wow.
I've got 4 cameras operating here looking in all 4 directions, and a friend of mine has some up at the Texas Astronomy site in Oklahoma also, so we sort of triangulate our activity.
Are those all sky cameras or something else?
Not all sky, they're just low cost Chinese cameras.
Gotcha.
But with multiple of them, you can get most of the sky.
Yeah.
What was that link again?
It's called Global Meteor Network. And so if you just I can do a search for GMN space status, but it may be because I've done it a lot and it's in my browser. But I think if you could do a search for Global Meteor Network space status, and you should get that page. That was a software package done by a volunteer. All this stuff is people that we're feeding the data back into research, but it's all volunteer type stuff.
Good stuff. I have 7 kids, lots of grandkids, and I've got 2 of my youngest daughters, Izzy and Lila, that just love to look at the sky. And I will share this.
Okay.
Yeah. I talk a lot about that, but let's go ahead on with the next thing. So here's our budget and dues. I'm not going to spend any time on how bad we need your renewals, but just to cover this again, let you stare at this. It looks like we're really only getting about 20 paid members, and we need your money just to survive and not continue the downcline. I want to show you that we did add the donation button to the homepage. there is another option if you want to send a check, but if you want to just click on a button and go through PayPal, this is on our homepage now. Please pay your dues. Here is the membership page as it is today on our website. It has a simple drop down. There's just two options. Individual is $20, families $21, and you can pay through PayPal, or you can also donate right here. The left-hand side shows the navigation page, and there's the fourth link down is the membership. So here's some next steps that we talked about last month, some things that I had to do. Place a donate button, that's done. Irving Club providing a micro grant. David is here. We're working on that, submitted some data on that.
They said, they told me there's a whole new board, there's a whole new, and that's fine. But I talked to those guys a week or so ago and kind of gave them a, hey, is this something? What do you think? Kind of a thing. And I got head bobs from them, and so they say February is when they would probably release it, right? So we should maybe work on something to get it ready for that February date. So we got some time to work on it, and I gave them a kind of an overview of what we were trying to do, and about how much we would want, and then the benefits, right? Multi-band, gigahertz beacon, and cover multiple bands, and everybody could use it in the DFW area. So it was good feedback from them. I felt good. So yeah, we'll continue working on it.
And by the same token, there could be something that NTMS could do for them.
Oh yeah, no doubt. They've got an event coming up in March. It's like it's at their bingo hall, right?
The Hamfest?
Yeah, it's a Hamfest, right, at their bingo hall. So be good to maybe come out and see them out there. And yeah, there's a lot that can be done with those clubs and some of the other clubs, I think, in the area as well. Yeah.
Sure.
Get some exposure.
Well,
get some more members, right? Like you guys are saying, there's about 20 reoccurring members in the club. It's barely self-funding, right?
No, it's not. And we're going through a period where the bank balance is declining every year. We process estates, let's put it that way.
Yeah.
Like somebody's got to take care of all this stuff someday. And so,
Right. Yeah, same here. Yeah.
Yeah. But we would like to be in a better position where that's not all that we depend on. But going back to how we could support Irving or other clubs is our knowledge is in a different area than VHF. Let's put it that way. So there could be something we could help them with. We could build something. We could connect some way with equipment that we have that would not be anything we would have to charge them for.
The Irving guys also have access to a giant tower right down there in Irving, and they've got all kinds of antennas and stuff on it. So maybe put a beacon down there. I don't know if that makes sense or not, but just throwing that out there. So yeah.
Yeah, exactly. We've got a few beacon deployment ideas. We do have access to one tower that's not in Denton. We have the unit that's at the top of the Texas Women University dormitory. So that's 280 feet high location. That's where our UHF and microwave beacons are currently located. We have that access, and we also have another new tower access that's in the Louisville area. And that's where we plan to deploy the tri-band beacon. There's also an ongoing legacy location in a town called Desert. It's not on the map. It's up by Scott. If Scott's still here, it's by a town called Frog Knot. But anyway, so we've got several locations, but it would really be helpful if we could access something in the Irving area. So that's another possibility. But I'm talking about something we could do for them, which would be leveraging what we can bring to bear. But we definitely want to support their activities like the Hamfest at the Bingo Hall. So count on us to be there for that.
Excellent. Yep.
Hey, Jim, I just had a thought. Since this group has unique skills, perhaps they could build something that would be of interest to VHF and UHF hams, because there's a lot more than them than there are microwave hams, and then raffle it off and go to the different ham clubs that would have an interest in VHF and UHF and raffle it off, because that way you only have to build one of them, but you can sell them to many people.
Yeah, okay on selling it, but I'd be willing to give it to them too. Is maybe like WSJT based VHF beacons, which are now well within our grasp, and we can build those and make those available. They're just a couple $100. So that's a good, that spurs me on. It sparks an idea, Ben.
No, I'm not talking about selling it to them. Sell raffle tickets and get many, many people to buy raffle tickets on one desired item.
Yeah, maybe so. Maybe so.
Speaking of raffles, the DARC has started their raffle for Summerfield Day, and they're raffling off a new 7300 Mark II. So you buy one ticket's $5, or you get 5 tickets for $20. And every year
that's
that we've
that's
done
HF plus 50 megahertz.
Yeah, it's a 7300. It's an HF radio. It's 6 meters and up to 160, right? It's the new Mark II, their new Mark II that just came out. But it's an investment. The club spends $1,500 for the radio, maybe less on a discount or a Hamfest sale, but it gets raffled off with ticket sales that start in January. And so we sell hopefully 500 tickets or more towards that. And so we end up raffling that off, and it gets people interested in the club. It gets them out to field day, and it also maybe generates a few $100 for the club.
And it funds the micro grants.
Well, the micro grants come from Irving Radio Club. This is for the Dallas Amateur Radio Club.
Okay, gotcha.
Yeah, I'm just using that as an example of how the raffles have worked for the Dallas Amateur Club. You're talking about raffling off something here, and if you can raffle something off and make some money on it, then that's awesome.
Maybe we should think more along those lines.
Well, you said you close out estates and stuff, so usually sometimes depending on the estate, that could include all kinds of goodies, right? And you can either sell it or maybe you start raffling it off.
But that depends on people dying.
Yeah, we don't like people dying.
I like Ben's idea better.
Yeah.
Focus on something people need that's current, and then raffle that off. And
exactly.
Okay, let's keep moving. I've got my wife knocking on the door over here. So there's another bullet point. There's a grant that could be obtained from the ARRL. That's a bigger task of due diligence. I need a volunteer for that if that's going to happen. I don't know that I'll get to it until after May when I retire. Okay, so let's talk about the election. This is the election meeting. I've not heard of any nominations. Matt Kuby, W5ZCA, asked to take a reprieve from the VP position. I just met with him last week. We had toad burgers at the Horny Toad Cafe in Cranfills Gap. We both operated a Rover down there. He wanted to take a break because his work has required him to relocate. He now lives in Brownwood, so it's just got him tied down right now. Al has volunteered for the VP position for 2026. We will be planning microwave update 2027. I will continue on as the president if there are no objections. I wanted to call out that there are several other people in the club that do work. Number one would be Scott Armstrong, AA5AM. Scott's kind of vigilant on bringing forward information of interest to our group. And he served as a vice president a year ago, but Scott just has this compelling interest in what we do. Eric is our treasurer. That's an appointed position. And Eric is our secretary. Wes is our treasurer. So if there are no objections, we'll just continue on like we are. I'll continue with the president position. Al will step in as the vice president to help with all items there, and which he usually does anyway, and also with the microwave update planning. Any other comments or conversation?
Jim, could you put on the front page of the web page that the dues are due?
From the website?
Yeah, on the website. Just
Yeah,
to
let me see what I can do about
remind
that.
people to send the money. And I make a motion, we adjourn.
I got a one comment here for Jim, or question for Jim.
Ed?
Yeah, I heard from a VE7 that apparently the guys over in Poland have got a new board design for the 24 gig rigs, and I'm not sure what they've upgraded, but I wonder if you've any idea what they've done that might be a benefit to us, or.
That's first I'm hearing of that, Barry. I had supplied them with the Gerbers because I didn't want to make another order yet due to the tariffs that I incurred the last order, and they were asking could they get boards from me, and I told them not till the tariff is not a problem. So I gave them the Gerbers. I'm not sure what new thing they've done.
I'll find the email and forward it to you, so maybe you can query the VE7. Dino was his name.
Great, thank you.
Quick question for Barry. Are you at your Canadian address?
Oh yeah, that's the only address I have now.
Okay, I'll send you some of the Vivaldi's.
Okay.
And to our El Presidente, you want to talk briefly about Microwave update 27.
I know that we need you to run the antenna range, Kent, and it would be helpful if you would pitch in with the gathering of the proceedings.
Okay, I've been VP several times, or have you already picked someone out for that?
Yeah, that's Al.
Oh, it is. Oh, amazing. Okay.
Yeah, I just spoke on that. Al has volunteered to be VP, so I think we're squared away on that. But I think you could really help us with the proceedings and of course, the antenna range. That's a given.
And I could get out my cattle prod and convince a few people to become speakers.
I would appreciate that. So we'll have some meetings coming up. It's 2027. It's going to be late in the year, but I don't think we can start too soon. So I don't retire until May 31st. So I'll have some limited participation until then. But once we get the venue selected early on, like next month, then I really would appreciate your help getting the proceedings pulled together and getting some speakers pulled together.
Retirement? What's that?
Yeah. I'm not going to go there. It's about the same as paid time off right now, which I call it pretend time off.
I tried retirement, but after 15 minutes, I got bored.
Yeah. Let's see. I think it was that Bob asked about this page. I'm showing it now.
Yeah, no, I meant right up at the front on the front page, make it so that if somebody goes to our site, they see a thing saying pay your dues.
Oh, okay. Right here.
No, right in the middle of the front page.
Yeah, right here.
Right there, yeah.
Okay. I'll change that and put it right up front above the software defined radio thing.
Yeah, make it bigger too.
I'm still trying to figure out how to send an HTML email so that I can actually send it to the whole NTMS groups IO that just has a clickable link. I'll figure it out.
How to do that. Yeah.
But yeah, I'll change it right here as soon as we're done, so that it's right up front. And we do want folks to pay for their membership. It's great that folks come to our club meetings and to the Zoom meetings, and they contribute and they interact. But we need the money. This thing doesn't work on, vapor. It has to have money, or we will run out of money. Or unless we get some people that die, we're going to run out of money. I heard you motion for adjourn. Anyone second that?
Yeah, V4MA.
Thank you, Barry. It was great having you guys here today. I really appreciate seeing the names in the list. Nice that Al could check in from KH6, and I will see you guys later. Thanks again.
7-3.
Thank you, Jim.
Thank you.
7-3.
Thanks, Jim.